Okay, the next point is once you have played with the wavelengths, which is a combination of the primary or secondary colors, and next is a mixtures. Now, here you can see that there is a what are the primary colors and what are the secondary colors and how these colors are combined to create the some other colors. And in a first figure here you can just see that there are basically uh, in a color image processing there are two basic models, and the models are there is a red, green, and blue. So your first model is R, G, and B, and the second model is a there is a yellow, magenta, and cyan. So this is a Y, or you can just say it as a there is a Y M C, or it can also be pronounced it as a C M Y. Or let that we will discuss in the upcoming slides. And these two are the basic models. And here you can see that once if you want to create the white color, which is a requirement of television. So in a television, so we need most of the RGB color models. But yes, so while we are doing the printing, there is no requirement to generate the white color. Once again, okay, there is no any requirement to generate the white colors in the printer. So in that cases, we can use the this particular model, and we can avoid this RGB, and which is more preferable. RGB model is more preferable in the TV, and where YMC is more preferable in the uh, printing printing task. So what are these top color models? The purpose of the color models, also known as a color space or a color system, uh, is to facilitate the specifications of the colors in the some standard ways and in essence. And a color model is specification of a coordinate system and a subspace within that system, such that each color in the model is represented by the single point contained in the subspace. And let us in upcoming slides we will discuss about this. And first the color model, and here you can just check it out. There is a green, and there is a red, and this triangle is representing the uh, color on a monitor, and how it will colors will reflect on a monitor. And they are very at a sharp at the boundaries, and where you can see that in a color printing, the in a color printing devices there is a represented by the shaded portion, and at each edges here you can just check it out. The various different colors are available. There is a green color is there, blue color is there, and the red color is there. And in order to create the bluish green, then it is the best. But if you want to add some red uh, in between the bluish green, then you can just tilt this point over there. So you will see the some different effect, which is a combination of the red, green, and blue, in which red and blue and green both are equal, but the red is a very minimum. So this is a type of illustration of a color. And next is let us begin with the first model, which is referred to as a RGB color model. And in a RGB model, each color appears in its primary spectral components of red, green, and blue. And this model is based on the Cartesian coordinate system. And here you can just check it out. There is a triangle is there, and there is a box is there. And here you can just see that there is a white color is available here, blue color is available here, and yellow. So the green color is available here. So there are RG. This is referred to as a RGB model. But yes, please note that if you are combining some data of a green and blue, then you will get the cyan color. And if you are adding the this red and yellow, red and green, you will get the yellow color. And if you are adding the blue and red, then you will get the magenta color. So if you are following this line, this is in a 3D. Once you get it in uh, if you will see this image in a 3D form, then you can see that at the exactly the diagonal point which moves from the this moves between the black and white is actually referred to as a grayscale. And how this color will look like, and here you can see that that is a actual representation of a color model, and all the values whatever we are using to represent an image that lie within that model in a 3D space. So the next is a CMY. CMY is CMY is referred to as a cyan, magenta, and yellow, which are the secondary colors of the light, and they are the primary colors of the pigments. So in this figure, and you can see that that is generating the RGB image uh, of cross-sectional color plane. There is three different colors: red, green, and blue. And the bottom one is representing the three hidden surface planes in the color cube. So please note that in order to generate a color image, you need a red, green, and blue, three different colors. And here you will see the uh, in a colorimeter, yes, there are three planes are there, which is in which you will put the one grayscale image, another grayscale image in a green plane, and the blue grayscale, this grayscale image into the blue plane, and then you will see all these all these images together in the form of color, and which is represented as like this. And if you are putting the R is zero, that is a red green is zero. If you are just using the green and blue, then you will get this kind of image. And if you are providing this green and using red and blue, then you will see this kind of image. And if you are providing blue, then you can see this kind of image. And in order to generate the CYM, you can simply do it by performing this operation. So this is only two models, which there are a lot of models, other lot of models are there, but yes, and these are two most common models which are used in a color image processing. Now there is another model is also there, which is referred to as a HSI, and HSI stands for the hue, saturation, and the intensity color models, which decouples the intensity component from the color carrying information in the color image. And in a result, the HSI model is useful tool for the developing image processing algorithms based on the color descriptions and that are naturally intuitive to human who after all the uh, developers and the user of these algorithms. And here you can see that in a figure there is a HSI color uh, HSI color model based on the there is a triangular there is a figure that is representing the color, and this is a here you can see that in a figure B you will see the circular color planes. So there are different color planes are available, and you can use any one of them. And this is a 3D representations of hue, saturation, and intensity. And now the next is a next important topic is a pseudo color image processing. Pseudo color is actually a false color image, which is totally different from the two color image. And this kind of image processing consists of assigning the colors to the gray values based on the specific criterion. Uh, the term pseudo files is used to differentiate the process of assigning the colors to the chromatic images from the processes associated with the two colors images. And we will discuss in upcoming slides. Just hold for a second. Just hold for a second. Okay, I will. Okay, where we are. Okay, I will give you the example a little bit later of a certain image processing. Mm. But specifically, we will just go towards. Okay, there is. Please note that this is a false color representation that I will explain you a little bit later. And first, we will do the intensity slicing and the color coding, which is also part of pseudo image processing, and the techniques of the intensity and the slicing, intensity slicing and color coding are the simplest and the earliest example of the pseudo noise processing of, so, not a pseudo color processing of digital images. And yes, here you can see that in this figure there is a 3D images given to you, and in order to represent that particular image, we will use the different slices. And here you can see that there is a first slide is already given to you, and this will assign the some different color. And that is definitely this is belongs to the one. There is one which is represented by white and black, represented by the zero, and all the values in between these two, black and white, is represented by the gray. And here you can see that this plane, that is this plane is very near to the one, so we can assign it as a 0 0.9. So just a random, so that we can understand the concept. And in the next plane, oh, okay, the next plane. Sorry, I'm able to make this. Just hold for a second. Yes. Okay, I will try to make it properly. Uh, so, yeah. And this is another plane, and which is just if this is a 0 0.9, then this is a 0 0.8, and your next plane will be 0 0.7. And in actual your entire 3D image is divided into the planes, and they provide the intensity at a different levels. For example, 0.8, 0.9, 0, and then 1, and goes on. And definitely you will get the gray level image at the end. And once you will check it out in the form of, if you will put the grayscale image into the colored format, then you will see the, here you can, there is a grayscale image, and this is a Picker thyroid phantom, and the another one is representing the result of intensity slicing using the 8 colors. So here they have used 8 colors, and you can just check it out. And the uh, yeah, that is exactly the this figure. That is a 3D representation, and if you will just see it from the top of the image, then the image will look like this. And the white is, this one is representing the higher portion, and there you can also see that there is a little bit higher portion is there, which is near to the white, and then it is reducing towards the black. So your end you will get the black portion. So this is a concept of intensity slicing, where we can use it in a practical format. And hopefully this concept is clear to you, intensity slicing and the color coding. And you definitely you can give the different color codes to these slices and these different slices. And so here you can just see the figure which will explain you the practical utility. Now the next point is the intensity to the color transformations. Now, in order to do that, the basically the ideas underlying this approach is to perform the three independent transformations, that is called red, green, and blue, on the intensity of the input pixels, and the three results are then fed separately to the these three different planes of the colorimeter. and this method produces a composite image whose color content is modulated by the nature of a transformation functions. So this is a concept of intensity to color transformations. There are three different colors involved, and once you have transformed, then you will see in a colored format. And here you can see that the representations. For example, there is a different planes are there, and this is another plane is there, and there is another plane. So there are two different planes are there, and once you will see it on a figure, then it will look like the color image. So this is the first year. Here it is also written there. There is a grayscale image in which the intensity corresponding to the average monthly rainfall. And please note that this is a color coding for this, and the color coding is for this is not provided. And the next is a color assigned to the intensity values. And the third figure is this basically. This third one is represented the color coded image, and there is a magnified image figure D, and that is over this portion. Now again, your entire concept is repeating, and this is a color coding for the multispectral images. And the multispectral images are nothing but yes, in some cases, mostly in the satellite images, we are using more than three bands. In multispectral means whose possible bands lie in between the 1 to 100. Means there are 100 different bands are there, and at a time you can see only three bands, and you can select accordingly, and you have to put the one band into the red and another band into the green, and this one band into the blue, and at the end you will see the red, green, and blue planes. And okay, and this time you can see only three bands, and it's up to you and what are your requirements. And this is a best example of a multispectral image, and here you can see that uh, there is a band which is required at a red wavelength, and this is acquired at a green wavelength, and this is acquired at a blue wavelength, and this one is acquired at a near infrared, and near infrared is next to the uh, R band. There is referred to as a IR. That is NIR. We actually say it as a NIR. NIRI band. And now this is a composite images. And what do you understand by the composite images? There is in this case there is figure E. We actually use the we have put the IR into the that is the infrared, that is we have put the NIRF plane into the red band, and then we have put this green. This is a green. We have put this green band uh, into the green plane, and we have put the blue band into the blue plane. And at the end, you will see the this kind of a image, and which is actually highlighting the vegetation area. And this is a land in which this is a river is there, and there is a little bit build up area is there, and you can see that the red portion is actually representing the vegetation area. And this, please note that this is a false color correction image, and the F figure is representing the that is a in which we have put we have put this uh, okay, and this one is a I will take the example form in which we have put the R into R, and we have put IR into green plane, and the blue, into the blue, and at the end you can see that the results, how it look like. And at last, there are some smoothing filters are there, and the smoothing and the sharpening filters, and we are using to smooth the image or the sharp the image. And the concept of smoothing and the sharpening is very similar to the whatever we have done in second or third chapter in the spatial domain filtering. And both concepts are same, and there is nothing special, and the only difference is the that is in which in a image smoothing we are applying over the three different planes, that is referred to as a red, green, and blue. And in a previous we are applying on a single band in whatever we have done in a spatial filtering. And these are the different RGB components. That is RGB. Once again, and here you can see that this is the RGB image, and this is a red component, this is a green component, and a blue component. And when we will see all these components, that is a red, green, and blue, then we will see the images like that. And this is the results of the image smoothing, and they have used 5 into 5 average kernel. And this is a and okay, the figure is representing the result of a processing of each RGB component image, and the next one is representing the result processing the results of processing the intensity component of HSA image and converting into the RGB, and the last one is representing the difference between these two images. And this is the end of the chapter for color image processing. And if there is any question related to that, then you can ask me. And in the next lecture, in the next one or two lecture, I will cover your entire syllabus. And after that, we will do the last two or three experiments, whatever the pending in the digital image processing lab. And uh, I already informed you that you have to submit your practical file of DIP by in soft copy form by 31st of October. And after 31st of October, there is or we can say it as on a next week, your evaluation will be conducted for DIP. And there is a okay, there is a quiz is also pending, which will also assign to you by next week, and you have to submit it on a same day when it will be provided to you. And yes, now if there is any question related to the color image processing, then please you can ask me. Otherwise, you can mark your attendance, and you can leave the session. And rest, if there is any question, then you can stay online and ask the question.